Unit 3, Lesson 2. So relationship between two quantities. Okay. So much of mathematics involves the search of patterns, relationship between sets of data. Many real-life applications of mathematics investigate the relationship between these two quantities. For example, the value of a computer is related to its age. Okay. The value of a computer and its age, obviously that's a regression. It's going to drop in price as you get older, just like a car. The price of a watermelon related to its weight. The heavier, the more expensive. That's a positive relation. And the time taken for a person to walk to school is related to the distance to be walked. Okay? So in mathematics, we call these relations. And when we relate things, that's what, in general terms, guys, that's x and y. We relate x and y in our functions. That's why a lot of things are in points, x, y, or y equals something of x. Okay? Those are all relationships. In this unit, we'll consider 7 ways in which relationships between two quantities can be represented. In words, mapping diagram, table of values, ordered pairs, an equation, a graph, and function notation. So these are the same 7 topics we're going to cover when it comes to relations. Okay, investigating a relation. Okay, I'm going to kind of summarize this, try not to read it to you exactly, but essentially the cost C of driving a car is related to the speed S as which it is driven. Okay, that's a relationship between the cost of driving at a certain speed. If you're going a faster speed, you're going to be using more gas, you're going to have more cost. Okay, that's a relationship. So we need to be good at, and what I want you guys to get good at, is identifying dependent versus independent variables. Independent is the one that determines the other. So for example, if I said you had temperature and time of day, which determines the other? Does temperature determine time of day, or does time of day determine temperature? Right? So if it's early in the morning, it's going to be colder. If it's midday, it should be warmer. So time of day determines the temperature. Therefore, your time of day is your independent variable. Or excuse me, independent variable. Temperature is your dependent. Okay? Time of day is independent because that is what turns the dependent variable of temperature what it is. Okay? So when we represent a relation, we often regard values of independent variables as inputs. Okay? So those are inputs, and I'll tell you, independent in general will be your x's. Your x's are your independent variables. Your y's will be your dependent. That's why they say input makes up the domain. The other thing I want you to know, domain, write this in your book, please. Domain goes with x, range goes with y. 20s still don't know that today. You need to know that for 20s especially. But domain means x, independent. Range means y, your dependent variable. Okay? A lot of just introducing things to you right now. All right, so now we're going to kind of look at all these different types of ways we can look at relations. Obviously, we would not attempt to collect every data possible for inputs. So we usually get a group of data, and then we kind of project. That's what a lot of people we do. So if you look, here's an example of a table. So if my input's 20, my output's 10. So that would be based on the pattern they're giving me there. So the pattern is input speeds of 20, 30 to 120. And it gives you the output of the speed. What's their output? I guess we're just inputting speeds. The output's how far you're going. Oh, the cost. Oh, we're staying at that same one. Sorry. So how fast you go and how much it costs you. Okay. So you can kind of see it's actually curved in this one. So 20 costs 10 and a 120 costs 10. What's that mean? When's your car the most efficient? Your car's most efficient at 70. This is like, almost idling. I know you're going really slowly, but if you're going slow, your car works hard to go slow actually because it's end up not using the full efficiency. So it wastes a lot of energy. And then when it's actually going with momentum, okay, and actual speed, it doesn't have to use as much energy. So it doesn't cost as much. But if you're going really hard, 120, then it's going to cost you about as much as 20. Anyways, it's just like a little bit of a curved relationship. That's why you see this curve right here. That's a curve. That's a parabola, right? Parabola. Parabola. Okay? Table of values, ordered pairs, graph, mapping diagram. So I think you're familiar with the table. Ordered pairs is just x and y. Okay, these are points. These are putting the points on a graph.
Junior class change.
And then the mapping diagram is just writing your values and mapping them. So 20 goes down to 10. 120 also goes to 10. Okay, and so just drawing where it goes in terms of outputs. Okay, so that's your four of your different relationships, ways you can demonstrate relations that was mentioned earlier, the 7. Any questions on how to construct any of those? And then a lot of these will be given. So they'd be given or you know the pattern. Okay, so you don't have to make these numbers up. Okay? All right, so then if we keep going here, we only chosen some of the possible input values. However, it's obvious that an output value could have been determined at any input value greater than 0 up to maximum speed of the car. So the car doesn't have a maximum speed. It can't go 1,000,000 kilometers an hour. So there will be a top out, okay, in terms of the fastest it can go. So this is the actual equation for the car. So that's what's given to us. You're not going to have to find that. You're not going to have to find that. You will in Math 20. I'm not going to show you now. Okay, so the graph of the equation of relation is given below. Keyword there is given below. Note the equation is only valid for certain input values, which make up the domain relation. So what happens is they're saying you have a domain. Okay, your domain is as far as it can go from left to right. Like the slowest it can go is 20. The fastest it can go is 120. So that's your domain, is between 20 and 120. And then we have values in between there. Okay? Values in between there. Okay? You guys have this graph on there, right? Like you don't have to draw it? Okay, so this page is done. Okay. Okay. All right, so this is again just talking about everything we just talked about. In an ordered pair, the values of the first coordinate are independent. Values of the second coordinate are dependent. Like I said, we're going to label these as x and y just to get used to it, okay? So independent is your x. Sorry. Dependent is your y. In a table of values, the independent variable is usually given first. The left. Okay, dependent is y. In mapping diagram, the arrows go from the independent x to the dependent variable y. On a graph, the independent variable is on the horizontal axis, x, often the x-axis, and the dependent variable y is on the y-axis. That makes sense. In an equation, we usually try to isolate the dependent variable, y, to the left side. So, generally speaking, cliffhanger, generally speaking, if I plug in something for x, it determines what y is, correct? That's what makes it independent. So if I said this is your relationship, I said x is 6. So you'd say, oh, x is 6. I can figure out what y is because x y depends on x. Excuse me. Y depends on x. So if I put a 6 in here, 3 times 6 is 18, minus 5 is 13, so y is 13. X determined y. Okay? So that's what they're telling you here in this labeling. Y is dependent. You didn't get all the way up there? Okay. So this section, this is the dependent. Values of the dependent variable represent the outputs from the relation. So outputs, think dependent outputs. And values of the dependent variable are represented by the second coordinate in an ordered pair on the vertical axis. So it is this coordinate, the second coordinate. Okay, x is the independent variable. The values of the independent variable represent the inputs of the relation. And then again, that is the this guy here. First coordinate in an ordered pair. Okay, moving along. Now we'll get to some examples here finally. Okay, so the diagram shows relations expressed in different ways. In each case, state the independent variable, state the dependent variable, list the inputs, list the outputs. Okay, so in A, Caleb, what's the independent variable? For A? Right, this group, right? So P is your independent. Okay, independent's P. So then what's your dependent? Q. So dependent is Q. Okay, and your list of inputs, 5, 8, and 11. Your list of outputs, 10 and 16. Okay. So Andy, on B, what would be your independent variable? Good. And then Denise, what would your dependent variable be? And then here's your list. You just write those for your inputs. These are inputs. These are outputs. Okay, for C, Aiden, what's your independent variable? Yeah, the big B. What's your dependent, Ridge? C. Okay, your list of your inputs will be your first number for all of them. So 3, 4, 5, 6 is your inputs. Your outputs will be your second number for all of them. 7, 11, 15, 19. Okay. All right, on the next one here. Diagram shows relations expressed in different ways. In each case, state the independent variable. So on A, what's the independent variable? Spencer, what do you think? I'll tell you pi is not a variable. Okay, so what's the independent variable? Okay, so remember variable. You're on the right side. R. Independent variable is R. 2 is always going to be a 2, so it won't change. So variable means it's going to vary. It's going to change. Okay? What's your dependent, Raj? Good. Dependent's that big C. Okay. How about on B? Noah, what's the independent on part B there? Yep, T for time. Good. And then Luke, how about the dependent? The height. Good. The amount of sap S obtained from maple trees is dependent on the time T a container left is attached to the maple tree. So amount of sap is dependent on the time. So this case, independent is T, because time will determine how much sap. Dependent is the sap. That's just one in words. Okay. Hopefully this is going smoothly so far for you. So in this section, we'll consider relations defined by an equation and sketch a graph by plotting ordered pairs. Make a table of inputs, choosing placements in the independent variable. for each of the input values, calculate the corresponding value and the dependent value, and then plot the ordered pairs on the Cartesian plane. So consider a relationship described by y equals 2x minus 5. So because my page is too big, guys, I'm going to do the table, and I'm going to have to lose the table, and then I'll do the graph, okay? So make the table first. So what we're doing is that they gave us inputs. Okay? I'm trying to figure out here, do we want to? Yeah, so you can kind of plug in some other points here, like whatever you want. Like we can do 5 and like 7, just try a couple other ones, just give us some more look. But you can; those are kind of open for you to try whatever you want to try. So if I input -2, this is the equation we're using. This is our relation, y equals 2x minus 5. So I have the inputs for x, so I put in values for x. So -2 times 2 is -4, minus 5 is -9. So this is -9. The point is -2, -9. That makes sense? See? Put -1 in. You're going to see there's a pattern. You're going to have to do this every time. 2 times -1 minus 5, that's -2 minus 5, that's -7. What do you notice? Well, let's do one more. If I plug a 0 in, 2 times 0, 0. 0 minus 5. So it's going up by how many? 2. So we can just finish this out. Okay, we'll have to plug this one in because that's not 3. See what I did there? It's going +2 each time. That's a relation. That is because of this 2. We'll talk about that later. But that 2 is causing that growth. 1, -3, 2, -1. We'll plug 5 in. 2 times 5 is 10. Minus 5 is 5. 2 times 7 is 14. Minus 5 is 9. So there's my table. Now we're going to plot the points on the graph. So I'm going to lose the table. Everybody have the table good? Okay, so our first point was -2, -9. So that means I go left 2, down 9. There's my first one. My second one is -1, -7. Next one, 0, -5. 0 means you don't move left and right at all. 1, -3. Right 1, down 3. 2, -1. And then we also did 5, what was it, 5, 9? No. 5, 5, thanks. 5, 5, and then we did 7, 9. So you can see this is a linear relation. It's a straight line. Okay. So plot the ordered pairs. We did that. Connect the points in the grid. Extend the line in both directions. Make sure you put arrows on there. That means it's going forever. Use the graph. Yeah. What? Oh, that's somebody. Oh, yeah. Extrapolate? Yeah. Okay. Use the graph to determine the value of y when x is 6. So if I go over here, 6, it's going to be, looks like 8. But I think mine's off a bit, actually. I think it's actually supposed to be right here. So it's actually going to be, oh, there we go. Well, that was cool. I just moved it. Made a little. So it's 7. No, yeah. So 6 goes to 7 for y. Use the equation in terms of the value of y when x is 6. We just did that. Oh, use the equation. So it's 2x minus 5. 2 times 6 minus 5. 12 minus 5 is the 7. says write the value of y when x equals 6 in the table above using the first blank. So we're supposed to use that. So above you can put 6, 7 in there if you want, or just put it in the side. It's not that important. We made our own up. How about this one? Says use the graph to determine the value of x when y is 3. So up there you have to go up to 3 for your y and find your line and come down. What do you guys get for that one? Correct. X is 4 when y is 3. And complete the following statement. The relation is called a linear relation. Almost done. Last page. Almost there. Okay. Consider a relation described by the equation x squared minus 6. This is the parabola. Okay. Complete a table of values to the right. Show some of the possible input values. What is 4 squared? Minus 6. 3 squared is 9. Minus 6 is 3. 2 squared is 4. Minus 6 is negative 2. 1 squared is 1. Minus 6, negative 5. Whoops. Zero, that's negative 6. Negative 1 goes back to negative 5. Because negative 1 squared is positive 1 again. And then it's back to negative 2. Remember, we talked about this a little bit. Parabolas are what? Symmetrical. So parabolas will always do this. Okay, we'll leave that box blank this time so they can tell us what to put in there. Okay, so those are our points. So go ahead and put those in the, plot those points that we just got. You'll see you'll get the parabola shape. Okay, so I'm going to have 4, 10. There's my first one. 3, 3. Second one. 2, negative 2. 1, negative 5. 0, 6. Negative 6. Negative 1, negative 5. So you can see your parabola. Put your arrows on it. Use the symmetry of the graph of the table to predict when x is negative 4, which I already did. X is negative 4. It's going to mirror. See how this right here is 1, 2, 3 away? 1, 2, 3 away. They have to be the same. They're symmetrical. We talked about that a little bit with you guys with parabolas earlier. And they're symmetrical because of the square. When you square a positive and you square a negative, you get the same thing. That's why they're symmetrical. It folds back on top of itself. Okay, so that one we got, yeah, 10. Thank you. An x squared. A parabola has to have a quadratic, which is something squared in it. But they obviously move, adjust in different ways. Use the equation to determine the value of y when x is negative 4, which we just have to plug it in. So we would go negative 4 squared minus 6. That's 16 minus 6, which is 10. Do you have a question, Maddie? You good?
I missed one.
Oh, okay.
That's why, yeah, I'm good.
Good. Write the value of y when x is negative 4 in the table. So write that value in there. So negative 4, 10. Put that in that spot in the table above. Connect the points in the grid. Smooth curve. Why do you think this type of relation is called a nonlinear function? Yeah. Negative 4, 10. No, sorry. Negative 4, 10 goes into your table for that last spot that's open in your table. See that open box? Yeah. Caleb? Question? Oh, you want to answer? Why is it non-linear? Right, because it doesn't go in a straight line, and also because it doesn't pass, like, if I can also draw a straight line through it and hit more than one spot. So if I do this, it hits 2 spots, that means it's not linear, because it's folding. It's coming back on itself. Okay, but good. It is not a straight line. Okay, that's it. A lot of table setting today. I know it probably seemed a little bit redundant,